All right, you guys, sorry for the interruption. I'm just picking up on Chapter 5.5, Continuous Random Variables and Intro to Normal Curves. So right here is where we left off, where I've drawn out that we're looking at a normal curve, which typically we have values that go between -3 standard deviations to +3 standard deviations. So the bulk of our data will cluster around the mean, and we see that the further away we move from the mean, the deeper we are in the tail regions, the more and more unusual an event becomes. All right, let's flip to the next sheet. All right, so right here, we are looking at the general rule or the empirical rule, which we often just call the 68, 95, 99.7 rule. So we're saying that right here, right where there's a 0, that's where our mean is, right? Because we're 0 standard deviations away from the mean, we are the mean. And then right here, we are 1 standard deviation above. Here we're 2 above. And here we're 3 above. Right here we are 1 below. Here we're 2 below. And here we are 3 below. So that 68, 95, 99.7 rule is saying this. Let me just get myself some Post-its. Okay. So 68% of our data, the bulk of it, should fall within plus or minus 1 standard deviation of the mean. As I move out to here, 95% of the data should fall within 2 standard deviations of the mean, because here's the +2, here's the -2. Okay, here to here. Okay, so most of our data, almost all of it, 99.7% of the data, will fall within 3 standard deviations of the mean. Okay, so then over here, I'm going to actually break it up into more specific regions. So right here again, there's the mean. Here we're 1 standard deviation above, 2 above, 3 above, 1 below, 2 below, 3 below. So again, first thing that I'm thinking about is that middle 68%. So if 68% falls within here to here, and this is a line of symmetry, an axis of symmetry, I'm just going to take that 68 and split it 2 ways to get 34. So that means that 34% of my data falls here and 34% falls here. Okay, now I'm going to move out to the 2's. So 95% of my data falls from here to here. So to get there, I'm just taking 95. I'm going to take away 68. And then I'm dividing it by 2. So that's really taking 27 and splitting it 2 ways, and I get 13.5. So 13.5% falls here, and 13.5% falls here. Okay, I'm going to move out even further. I'm going to go to the 3's. So 99.7% of my data should fall within these 2 markers here and here. So I need to take that 99.7, take away the 95, and then split it 2 ways. So it's really taking the 4.7, splitting it 2 ways, which gets me 2.35. Okay, so 4.7 split 2 ways is 2.35. So I have 2.35% that falls here and 2.35% that falls here. Okay, so if those 2 markers here to here account for 99.7% of our data, then I'm just taking here that last 0.3% of the data, splitting it 2 ways and getting 0.15. So I have 0.15% that would fall here and 0.15% that would fall here. So again, it makes sense that it's highly unusual to have data that falls beyond those 3 standard deviation markers, right? It's not impossible. It would just be highly, highly unusual. All right, so some common examples of normal distributions in the real world. So we're looking at any sort of model that would produce that bell-shaped curve. So often we think of standardized tests. Let me just slide this up. So standardized testing, so SAT, ACT, IQ GRE, that's for grad school. Manufacturing processes, so when we think of the diameter of a bolt or the length of a bolt, when we think of lifespan for a light bulb or battery. Okay, a lot of things that exist in nature or exist in terms of human animal characteristics. So height, weight, skull circumference, but specific to gender, age, and species. So all of those we're saying are roughly normal. So when we visualize distributions of data, it should again look bell-shaped and symmetric. All right, so considering our normal curves shown below. So here we have 3 of them. Which one has a greater mean? So when I'm looking for the mean, I'm just looking at where would be right smack in the middle of the distribution. So right here for A and C, it looks like they have the same mean. Right here, the mean looks like it's about 45. And then for B, right here, the mean looks like it's about 60. So B has the biggest mean. The mean is 60. Okay, and then what about standard deviation? So when I look at my 3 models, I can see that, well, it's got to be C because it's the most spread out. But if I'm trying to estimate what it is, so I can see that, well, that looks like 30 to 60 right here. So here was the 30, and here's the 60. So when I think about what that span is 30 units. And if I split it 6 ways, that would give me a standard deviation of 5. So C has the biggest standard deviation, right? It's about 5. So here again, how did I get to that figure? Well, right here would have been my mean. And then up here would have been the +3 standard deviations. And here the -3 standard deviations. So if I add in those little notches, right, I'm splitting a third here and thirds over here as well, then I can see, oh, I have 6 little notches all the way across, right? So I'm just splitting, again, that span of 36 ways, and I get to 5. All right, next up here, the heights in feet of fully grown white oak trees are normally distributed. The normal curve shown below represents this distribution. So find the mean height of a fully grown white oak tree. Well, that's pretty obvious, right up there. So the mean, it looks like it's 90 feet. Okay, and then getting a standard deviation, well, if I look at the span from here to here, that span would be 3 standard deviations. And I can see that that span from here to here looks like it's about 10 units. So if I take the 10 units and I split it 3 ways, that gives me about 3 1/3. So my standard deviation, it looks like it's about 3 1/3 feet. All right, one more page. So flip it over or pull out that last page. And here we go. So here, I wanted you to fill out the normal curve in the same way that I did it on the previous side. So I want you to take a moment, maybe pause for a second, and see if you can fill it out. Okay, and then unpause when you're ready. And we should have here the mean right smack in the middle, right? We're 0 standard deviations above or below. We are the mean. Here we're 1 standard deviation above, 2 above, 3 above, 1 below, 2 below, 3 below. Okay, I'm going to draw in those little dotted pathways like I did before. Okay, I know that from here to here, that's 60% of my data. So if I split it 2 ways, I have 34% here and 34% here. Okay, as I move out, 95% of my data, but take out that middle 68, split it in half, and I get 13.5% and 13.5%. Keep moving out. Okay, here's my middle 99.7%, but take away that 95, and I'm left with 4.7, and that splits 2 ways. So I have 2.35 here percent and 2.35% here and here. Okay, and then all the way out should be 100% of my data, here to here, that's the middle 99.7. So I'm splitting that last 0.3% two ways, and I get 0.15% and 0.15%. All right, so now we're answering questions. So what percent of the area under a normal curve lies to the left of the mean? Well, that should be just 50%. All right, to the right of the mean minus 2 standard deviations. So we're saying to the right of right here. So if I add all these up, I can get to 97.5. But I could also take away this 2.5 from 100. Either way, I should end up with 97.5%. All right, now we're saying between the mean minus 1 standard deviation right here and the mean plus 2 standard deviations right here. So if I add up these three regions, right, I got the 34, and the 13.5, I get 81.5%. Okay, and then lastly, more than 3 standard deviations from the mean. So it's implying away from the mean. So let me draw a little normal curve like this. Let me mark where those extremes are. So the minus 3 and the plus 3 standard deviations. And remember, here's the mean. So if I'm saying more than 3 standard deviations from the mean, more than I'm moving away from, I'm looking at those two tail regions right here and here. So I'm really adding up those 2.15% regions, which gets me 0.3% right here. All right, one more problem. So the lifespan of a battery, let me slide it up. The lifespan of a battery is normally distributed with a mean of 2,000 hours and a standard deviation of 30 hours. Sketch a picture of this normal curve, mark the change of curvature, the inflection points. Okay, so first I'm just going to say, okay, here's my mean. 1 standard deviation above, 2 above, 3 above. Okay, 1 standard deviation below, 2 below, 3 below. Okay, I'm going to transfer all of those percentages down. Let me just add in my dotted segments like so. So here I have 34%, 34%, 13.5%, and 13.5%. 2.35%, 2.35%, and then those tiny little slivers out in here, 0.15%. Okay, my change of curvature points would be at 1 standard deviation. So right here and here would be my change of curvature or inflection points. And then I have to add context. So my mean is 2,000, right? 2,000 hours. The standard deviation is 30. So if I add 30, I get 2,030, another 30, 2,060, another 30, 2,090. Okay, take away 30, I have 1,970. Take away another 30, 1,940. Take away another 30, 1,910. Okay, so now I'm answering questions about my diagram. So here I'm asked, what percent of batteries last less than 2,060 hours? So here, I'm looking at what are these percentages added up. Okay, I could add those up, or again, I could take 100 and subtract away this 2.5. Either way, I should get to 97.5%. Okay, what percent of batteries last more than 2,090 hours? So I'm looking at that little marker and then everything above it, that tiny little percent, 0.15%. Okay, what percent of batteries last between 1,940 and 1,970? So here we're just looking from here to here. So 13.5%. Okay, what percent of batteries are more than 2 standard deviations above the mean? So more than 2 standard deviations above the mean. So here I'm just looking at where is 2 standard deviations here and here, but it's saying more than 2 and above the mean. So I'm really just looking at this region up in here, and I would say 2.5%, 2.5%. Okay, what percentile corresponds to a length of 2,060 hours? So percentile, we're looking at the proportion of values that are at or below a certain value. In this case, we're looking at a lifespan in hours. So we're looking at the 2,060. I'm looking at that marker right here, and I'm looking at, well, what's the percent that falls at or below? So I can see if I add that up, looks like it's 97.5%. But when we're talking about a percentile, we always round the nearest whole number. So I would say that would be the 98th percentile. So about 98% of batteries live to be 2,060 hours or less, right? That's what that means. Okay, and then lastly, if 1,000 batteries are randomly selected, how many will last between 2,000 and 2,060 hours? So I'm looking at from here to here, what is the proportion that would last between those two lifespans, 2,000 and 2,060? So I can see, well, that looks like 47.5%. So I'm going to write that as a decimal, 0.475. And then I'm going to multiply it by 100, or not 100, 1,000, right? It's 1,000. So 1,000 batteries. So take the 0.475, multiply it by 1,000, and we're going to end up with 475 batteries. All right, I hope that process made sense. I will circle back tomorrow when we add a layer, when we move on to chapter 5.6. All right, I hope you guys have a great day.